Hey everyone, today we are starting a new unit. Today we are starting time-dependent um, circuits with capacitors and inductors. So there's going to be a bunch of differential equations in this unit. So I highly encourage you to go look up some other videos in differential equations, or if you have differential equations experience under your belt, that's good for you. If not, we're still going to go through this, and hopefully you may be able to get some insights into your differential equations class. All right, so let's jump right into it. The first time-dependent component that we are going to look at is the capacitor. Now, a capacitor stores charge, okay? So that is what a capacitor does. Here are the important formulas that go with it. The current going through a capacitor is the capacitance, C, which is going to be in microfarads or millifarads or some kind of form of farads. Okay, that's the unit for capacitance. With respect to voltage, voltage with respect to time, right? So the rate of change of voltage with respect to time. And for voltage, the other way around, it's just the integral of that, 1 over C, and then integrate the current with respects to this dummy variable, and we put t into that dummy variable, so with respects to time, okay? And our other new component is the inductor. Now, an inductor maintains current, so it appreciates the status quo. You have current going in through here. After a long time, the inductor will love to keep the current going, okay? And the important formulas are the voltage is equal to the inductance. So this is inductance. And inductance will be measured in microhenries, millihenries, or henries, okay? And the rate of change of current with respect to time. And to the opposite, to get the current, we have to have the same thing, integrate 1 over L integrated over voltage plus some arbitrary starting value. So we have some arbitrary starting value here. Now I have some important facts for you to know about these components, and I would highly recommend you memorize these, and you can build up your own intuition about this, especially if you have taken E&M. So important fact number 1 is when a capacitor is in a DC environment for a long time, it behaves as an open circuit. Think I of t is equal to C dV dt, okay? Now what do I mean by that? So right here, we say that an infinite amount of time has passed, okay? And because while an infinite amount of time has passed, the rate of change of the voltage stops, right? Because what a capacitor really does is it takes electrons right here and it stores them across this guy right here, and so there's a voltage difference right here, a voltage difference, so a change in V between these two plates, and soon enough there becomes so much charge right here that the voltage difference doesn't change anymore. And if there's no more voltage difference, then that means that it's going to be the derivative of 0 with respect to time, which is just 0. So then that means that the current, is 0. And what do we know? What is a circuit that we know where the current is 0? An open circuit. So open circuits, right, they have no current going through them because there's this big blockage, right? Some high level of resistance between this point and this point, and the voltage difference can't change anymore. Now, fact 2. voltage across a capacitor cannot change instantaneously. Now, for this, think of like water, okay? Say that you have a cup, right? And someone is filling up the cup, right? Well, you're going to start at zero amount of water, right? And then you're going to fill up little by little up until you get to the full capacity, right? That's how a capacitor works. And you can't have an instantaneous amount. You can't just have a cup of water and then immediately it's full, okay? That's impossible. That cannot happen. So, thus, we know that the voltage at the voltage coming up to 0 from the right side is going to be equal to the voltage coming up from 0 on the left side. And this is just basic calculus right here. That means that the limit does exist. The limit does exist, and it's continuous and it is differentiable. Okay. Well, actually, no, I take that back. It's not necessarily differentiable. It's just that the limit here exists. Okay. That's number 2. Number 3, when an inductor is in a DC environment for a long time, it behaves as a short circuit. Now, we're going to think about this equation once again. Well, not really this equation, the equivalent of this equation, but for inductors. So the voltage equals the inductance times the rate of change of current with respect to time. Okay. So let's think about this. After a really long time, we have just a regular amount of current going through, right? So the current no longer changes because originally this inductor in a DC environment, it did want to oppose this, right? We know this from basic E&M. We know that an inductor doesn't like change. The inductor, when this power source was turned on, originally did not want the current going through this, right? It was a very high resistance. But after a long time, eventually it got used to it and it tended to like the current. And so once the current became constant, like some constant C over dt, well, that's just 0, okay? So then that means that the voltage difference is 0. So as opposed to this one, where the current was 0, the voltage difference is 0 here. And what do we know about something that is that it has a voltage difference of 0? Well, it's directly connected to ground, right? That means it's just a simple straight wire. So the inductor acts as a short circuit in a DC environment after a long period of time. Okay? And finally, number 4, current across an inductor cannot change instantaneously. So the limit exists between 0 plus and 0 minus, or more generally t plus and t minus if you're not stationed at 0, but for our intents and purposes, we are going to be centered along 0 for the entirety of this intro stuff, or at least that's how I was taught. And this you can also think of intuitively. This inductor has to get used to a current, right? And the inductor can't get used to something instantaneously, right? Just like how the capacitor can't get full immediately, the inductor can't just be okay with the current immediately, okay? So that's where we get this right here, okay? So make sure, like, take a screenshot or something, write these down, because we're going to be using these ideas for the entirety of this unit, okay? So we're going to go ahead and do some practice problems. All right, let's do this. So right here we have a circuit, a very simple circuit, and you can actually solve this with E&M techniques, but we're going to solve this with circuit analysis techniques. So when you are solving these kinds of time-dependent problems, or problems with components that vary on time, you are always going to have 2 scenarios. You're going to have the scenario from negative infinity to t, and then the scenario from t to infinity, right? And infinity is a relative thing, right? Depending on, this capacitance and this resistance will determine what is a very long time. That could be 8 hours, it could be 3 seconds, etc., etc. So, when doing this, and I'm going to try to be very, very, very methodical in this because I can tend to skip around with this, especially after doing this, so many times for tests and whatnot. But I do make a lot of mistakes regardless. So, step one is we are going to redraw the circuit. Okay, we're going to redraw the circuit when it is negative infinity, right? From negative infinity to t. So all of that time up until this, oops, I forgot this switch. Oh yeah, and I forgot to mention that these kinds of circuits, at least the differential equation ones, are going to have switches, okay? Because we're going to turn on and off the voltage sources so that these capacitors and inductors will react differently in different environments of voltages and currents, etc., etc. Okay? So originally, the switch was closed, and then at time equals 0, the switch opened, okay? It just opened like that. So we want to figure out what was the circuit doing when the switch was closed, okay? So before it opened, right? So we're going to go ahead and draw the circuit again. Okay, and I'm going to just draw the switch as if it's closed. I'm going to label this A so that you remember that there's a switch right here, okay? There's a switch right there. Now, we still have this 5-volt battery, and we still have this 10k ohm resistor. But remember what we said? Remember how one of the important facts is when a capacitor is in a DC environment for a long time, well, negative infinity to t is a pretty long time, it behaves as an open circuit. So then that means what was once here a capacitor is now just an open circuit, okay? And I'm going to just label this right here as being the capacitor. I'm not really going to write anything there. So yeah, now let's figure out everything that's going on in the circuit. So first of all, everything at this point is going to be V of 0 minus, okay? Because it's everything leading up to 0, okay? Like if you have a graph, right, it's going to be everything it can be doing, I don't know what it's doing, up until it reaches 0, okay? That's all we care about for right now because we're only looking at the negative infinity portion, okay? So what is it doing, right? What is this capacitor doing? Well, it just has a voltage difference across it as 5 volts, right? Because it's completely open, and we have 5 volts here, but we have ground down here. And sorry I didn't write ground, but it should be implied, right? We have 5 volts here, right, across. So this resistor completely dissipates those 5 volts, okay? So across this capacitor, there's a 5-volt voltage difference. So we can say 5 volts in V of 0 minus. Can we say anything about the current? Well, yeah, we can. What is the current looking like? Well, all we have is a battery and a resistor in series, right? So we're just going to do Ohm's law, and we're going to have 5 volts over 10k ohms, and that is just simply 0.5 milliamps, okay? Is there anything else that we know? Well, let's go look back at our facts. This looks right. Voltage across a capacitor cannot change instantaneously. Well, if we figured out what the voltage was across this capacitor at V of 0 minus, then because it's a capacitor, we actually know what V of 0 plus is. And we know that V of 0 plus is 5 volts. Okay? Now, do we know I of 0 plus? No, we don't. There is no fact or anything that this current can actually jump instantaneously, and I'm sure that there's some theoretical thing proving this, but for the sake of this video, we're not going to go in depth with that. Okay, so now we know everything that we need to know from the negative infinity portion. Okay, and I have a tendency to solve for both the 0 minus values for the voltage and the current. We may not use all of them, but I like solving for them because just in case I do need them. So step 2. So the next step, we found the negative infinity portion. Now we need to find, we need to find the positive infinity portion. Okay, and now the positive infinity portion, let's see what that looks like. Well, first of all, this switch has been opened. So then that means this battery is no longer a part of the circuit in the negative, the positive portion. And so our circuit will simply be a capacitor and the resistor. And I forgot what it was. 10 microfarads? Yep. 10 microfarads. Okay. So we still want to find the voltage here. And the voltage here is the same thing. It's like all V of t, right? Now, what is an analysis that we know that we can use to solve this? Well, a nodal analysis. Okay. So what we're going to do is we're going to find a nodal analysis down this way and a nodal analysis down this way. And we know this is ground right here. So we're going to have N1 here and V minus 0 over 10K plus, and do we remember what our thing was? It was 10 microfarads times dV dt, but I'm not going to write it as dV dt. I'm going to write it as V prime because I like it better, and it's I know it's with respect to time, and equals 0. Okay, now let's go ahead and solve this. We're going to multiply both sides by 10K, so it's going to be V plus 10 to the 10 times 10 to the negative 6 times 10 times 10 to the 3 is going to be 0.1. V prime is equal to 0. And I like to write my V prime right here. And we're going to divide everything by 0.1. And it's going to be plus 10. V is equal to 0. Okay? Now here's where we get some differential equations portion. So step 3, solve differential equation. Okay? And we're going to say, so when you see this right here, we see that it is it's equal to 0. So that means that this differential equation is homogeneous, right? And because it's equal to 0. Okay? That means that we can, I'm going to write this in blue because this is differential equations, but recall that dx dt plus px, some arbitrary p, is equal to 0. And once we integrate through, we're going to see, or once we solve it, basically, we are intrinsically integrating. X of t is equal to k, some constant k, e to the negative pt. Okay? And I'm going to go ahead and just prove that to you guys, even though this is not a differential equations class. I think that it would just be helpful because, yeah. Anyway, um, we're going to do a separation of variables. So dx dt equals negative px, right? We're going to move the px to the other side. Then we're going to divide both sides by x so that we can divide and multiply. Divide by x, multiply by dt. We're going to get dx over x is equal to negative p dt. And we're going to integrate, okay? The integral of 1 over x is just the natural log of x. And then we are going to have some constant c, but I'm going to go ahead and leave that off for now because this side is going to create a constant c, and we might as well just have it all in one c, right? Then we are going to exponentiate both sides, and we're going to get x of t, and we can remove these brackets now, is equal to e to the negative pt plus c. And remember from our exponent identities, it's e to the negative pt, e to the c is equal to this guy, right? Because the exponents add up. And this guy right here is just a constant, and we're going to call it k. Like so. And yeah, so instead of x this time, we're going to plug in v. And so v of t is going to equal to k e, and what is p in this case? Just 10. E to the negative 10t. Okay? And that's it. But technically not. We do not know what k is, but we can solve for k. Why? Well, we are in the step 4, solve constant, right? And remember at which portion we are at, okay? We are at the t to infinity stage. Therefore, we're on the right side of origin, the right side of the origin. Sorry, I'm tired, guys. So we are going to use v of 0 plus, okay? And v of 0 plus is just 5 volts. So we're going to say v of 0 plus is equal to 5 is equal to k e to the negative 10 times what? Times 0, because 0 is 0 on both sides, right? And so e to the 0 is just 1, so we get k is equal to 5. And so we get v of t is equal to 5 e to the negative 10t. And this is our answer. Just some housekeeping notes. This is an RC time constant, right? This right here is the time constant. And this is the guy that will determine how long is a long time, essentially. And so when we draw our graph here, and it will be very useful to draw graphs. Remember, we said that we got 5 volts from negative infinity to t, or yeah, well, t is 0 in this case, and this axis is t. And we have infinity this way. And so what happens if we plug in 0 into there? Well, we get 5 right here, which is consistent because we said that 0 plus, v of 0 plus, is equal to 5, and we said that v of 0 minus is equal to 5. And once we increase in t, as t gets closer and closer to infinity, this is actually v over e to the 10t. Well, if we get a really, 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 really big number up here, then that means we are approaching 0. And so our graph will look like that. And eventually, the capacitor will run out of charge, and it can no longer create a voltage difference across the 10 kilo ohm resistor. Okay? So that's it. But you may be wondering, I didn't use this current right here. Well, we can solve this exact same problem with a loop analysis. And I'm going to go ahead and do that real quick. All right. So I went ahead and copied and pasted the first part of this problem, and we have our, current source right here. But instead of doing a loop analysis, I mean, no, instead of doing a nodal analysis, we're going to do a loop analysis. Okay. Now, once again, the direction of loop completely arbitrary. I'm going to go ahead and draw my loop like this. Okay. And now this is ridiculously important. You need to make sure that when you're doing the opposite thing of what you should normally be doing to solve it, so like for example, it's very natural in a capacitor to use a nodal analysis because you're trying to find the voltage normally, right? Or well, actually, sorry, that's false. You're trying to find a voltage, you would rather want to use a nodal analysis than a loop analysis, right? And vice versa. If you want to find the current, then you're going to use a loop analysis instead of a nodal analysis. Okay. Well, right now we're trying to find the voltage with a loop analysis, so we're going to need a little bit of extra information. And one of that information is, what is the polarity of this capacitor? Well, the polarity of this capacitor is plus on top and minus on bottom. Why? It's because we had a voltage difference across when it was charging, right, in the negative infinity portion. It was charging with the 5 volts right here and ground being here. Okay. And this is important because we need to know the direction by which you know by which our current is going into this capacitor, because the capacitor is essentially it's a power source. It's like a battery. Okay. So we're going to go ahead and perform our loop analysis. So that's what step 3, or I'll call it. I'll say it's part of step 2. So loop 1. And our loop analysis is going to be, we're going to go through the 10k ohm resistor, so 10k I plus, and we're going to go through here. Now, here is the catch, and I did not get this until basically the end of the differential equations portion of circuit analysis. But the equation says a plus, right? This is a plus naturally, okay? But this right here, this is the forcing part. This right here, these constants, these are dependent on sign, because this is how the battery is starting. This is how the voltage is starting. This is how the current is starting, right? So what's going to happen right here is we are going to have plus 1 over C, which is 10 microfarads, 0 Ti, and then the dummy variable, sigma, d sigma, minus, okay, well, actually, technically, I'll go ahead and keep the plus right here. But we need to remember that this is going to be minus. And this is going to be minus because we're entering the negative side of the capacitor, okay? Now, this is all nice. However, we need to find I of 0 plus, because we don't know what I of 0 plus is. How are we going to solve our differential equation completely, that is, get rid of the constant, if we do not know the 0 plus portion? Okay? So what are we going to do? Well, we're going to solve for I of 0 plus by simply introducing 0 plus into this equation, right? We're gonna solve for what it is at t equals 0 plus. And so here we're gonna have an integral to 0 plus I, and then the dummy variables. And then I'm gonna go ahead and put the minus now. Minus v of 0 plus is equal to 0. Okay. Now, this term right here looks scary, right? Well, it shouldn't be, because this is going from 0 to 0, okay? Or 0 plus. So all of this is 0, and it just cancels out. And so we are left with 10k I of 0 plus is equal to, well, plus minus V0 plus. And we know what V0 plus is. That is just 5. So get rid of this plus, 5 equals 0. And we get I of 0 plus is equal to 5 over 10k, or is equal to 0.5 milliamps. Now you may be wondering, Alex, like we got 0.5 milliamps. Well, this is 0.5 milliamps. Well, remember, there is no rule for a capacitor saying that this has to be true. Okay? For all we know, depending on the configuration of this circuit, across this capacitor, it could be 0.8 milliamps, right? I don't know what kind of configuration would make that, but that's totally possible. And we're going to see some problems like that in later videos. I'm going to do a ton of differential equation, time-dependent, time-varying, component problems. But this one is just a simple example so that you can make sure that you don't make this mistake right here. Because I made this mistake so many times, and it was absolutely insane. So now we know I of 0 plus is equal to 0.5 milliamps. Okay? And now that we know that, we can go ahead and comfortably differentiate, because we want to take this I and we want to put it in a form that is usable so that we can find the voltage. Okay? So we're going to take this guy right here, our big, nice nodal analysis, or loop analysis. I'm going to copy it. I'm going to paste it. And we don't like this integral here, so we're going to take the derivative of everything. And we don't care that this is -5 anymore because it's a constant. Once we take the derivative of everything with respect to time, we're going to get 10k I prime plus 1 over 10 microfarads, and the derivative and the integral are inverse, so this is just going to become I of t equals 0. And we are going to get, by dividing everything out by 10k, we are going to get I prime plus 10I equals 0. Okay? And using our little trick that we proved earlier, we are going to get ke to the -10t. Okay? And now we can solve, so this is technically step 4. I believe it's step 4, step 3. Step 3. Differentiate. Okay? Now step 4, solve for k. So we're going to have I of 0 plus, because we found that, right? We found I of 0 plus. That is no longer question marks, but 0.5 milliamps. And so we're going to go ahead and say equals 0.5 times 10 to the -3 is equal to k e to the -10 t, not t, 0 plus times 0 plus, and we're going to get k is equal to 0.5 milliamps. Okay? And so we have I of t is equal to 0.5 times 10 to the -3 e to the -10t. Now that's fine and dandy. We found the current, but that's not what we wanted, right? So we're going to have to find a dependency. And what is the best dependency that we know? Well, we can find V of t right here because we know I, so we can just use the current, or Ohm's law, some variation of Ohm's law, from this node right here, and we're going to say V of t minus 0, right, because we're going down to ground, divided by 10k is equal to 0.5 times 0.5 milliamps e to the -10t. Okay? And remember, this is 10 times 10 to the 3. okay? And so we're going to get V of t, and 10 times 10 to the 3 times 0.5 milliamps is simply 5 e to the negative 10t. And just like that, we get the same answer. So in this way, instead of doing, power checking, which you probably could, we are checking by using either a loop or a nodal analysis. The loop analysis for finding a voltage was much more difficult than the nodal analysis. There's a lot more bookkeeping, right, to take account. We have to think of the direction. Because of this right here, you could get it wrong, and I've gotten that wrong so many times and stuff like that. And then you have to come up with a Ohm's law equation right here to find the same thing. But if you have extra time on your tests or you want to check with your homework, this is the best way to do it. And it also helps you practice your loop analysis. Okay? One more thing. A great way to check your work at the beginning is you should always get, when you have your equation right here, you should always get this, right? You should always get the correct corresponding plus on this side, because if this is minus right here, then that means the exponential will just, the graph will look like this. The exponential will keep going up. We want the exponential to go down, because if you can build a capacitor that does this, you should be given a PhD and a Nobel Prize. Okay? No capacitor with time gains charge without being charged itself. Okay? That doesn't make intuitive sense, but yeah. And you should also see that you get 10, which is the same RC time constant right here. Okay? And if you don't get that, then you probably need to recheck your work. But other than that, that's it for today's video. It's a very long video. Next video, we're going to do an inductor problem, and we're going to do some other more tricky problems. And so, yeah.